Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for just a second that you've just landed the ultimate remote construction job.
Oh boy.
Right. You have been hired to build a house. And not just a shack. We're talking a highly advanced, incredibly sturdy, literally life-saving shelter. But there is a massive, seemingly impossible catch to this gig. The nearest hardware store, the absolute closest place you can go to grab a 2x4 or a bag of cement or even just a handful of nails, is exactly 238,000 miles away.
Which is a rather long commute.
A terrible commute. You're standing there in this completely barren, airless, absolutely silent landscape. You are surrounded by nothing but gray dust and jagged rocks, and your boss basically taps you on the shoulder and says, "All right, start building." Oh, and by the way, if these walls aren't perfectly sealed and structurally sound by the time the sun goes down, you won't survive the night.
It sounds like a stress dream, honestly. But that is the exact kind of mind-bending reality that aerospace engineers are grappling with right now.
Exactly. We are looking at the literal foundation of humanity's future in space today. We're taking a deep dive into some truly groundbreaking research coming out of The Ohio State University.
Yeah, led by researchers Sis and Sarah Wolf.
Right. And featured on physicist.org, originating from Acta Astronautica. The mission for our deep dive today is to explore exactly how scientists are figuring out how to take that barren, gray moon dirt and turn it into highly durable structures using incredibly advanced laser 3D printing.
And not just the printing itself, which is complex enough, but the hidden variables no one thinks about.
Right. We're going to break down how this technology actually works. We'll look at why the specific ground you choose to print on turns out to be the ultimate secret to success. And we'll explore how mastering the art of construction in the harsh, unforgiving vacuum of space might just be the exact key we need to save our own precious resources right here on Earth.
Okay, let's unpack this, because the sheer scale of the problem these researchers are trying to solve is it's staggering. It requires a complete fundamental shift in how we even conceptualize the act of building. Think about it. When you construct something on Earth, you take your entire environment for granted.
What do you mean, like taking gravity for granted?
Gravity, absolutely, but also the atmosphere. You assume there is air to help regulate the temperature of your tools, your materials. You assume your building materials like steel or lumber are relatively uniform and predictable.
Right.
The Ohio State team is tackling a scenario where absolutely none of those earthly assumptions apply. None of them. They are trying to develop a fabrication process that can take the natural, incredibly harsh environment of the moon and use it to manufacture small, heat-resistant objects.
Which is the crucial first step toward building sturdy, non-toxic habitats and tools for future astronauts.
Exactly.
But to even begin that kind of research, I mean, you need the raw material, you need dirt, and you can't just requisition a dump truck full of actual Apollo moon dirt to run hundreds of experimental 3D printing trials in an Ohio lab. Right?
Definitely not, no. Real lunar regolith is one of the rarest, most highly protected and precious materials on our planet.
Yeah.
The Apollo missions only brought back a tiny fraction, and it's locked away in vaults for highly specialized analysis.
Yeah.
It's not for industrial stress testing.
So they use a stand-in.
Right.
The researchers utilize something called lunar regolith simulant, which is essentially fake lunar soil. It's a synthetic version of the fine, dusty material that covers the moon. And what really blew my mind was learning how incredibly specific this fake dirt is. They used a simulant called LHS-1.
Yes, LHS-1. The LHS stands for Lunar Highland Simulant.
Right. This isn't just, generic gray sand they picked up at a landscaping supply store.
Far from it.
LHS-1 is meticulously designed to replicate the specific soil found in the lunar highlands. And the highlands are described as this heavily cratered area rife with dark-colored basaltic rock. But I think we really need to visualize this before we get into the lasers and the printing. What are we actually talking about when we say heavily cratered area rife with dark-colored basaltic rock?
Well, what's fascinating here is how specific and challenging that particular geological profile is for a manufacturing process. When you look up at the moon for your backyard, you see lighter areas and darker areas. The lunar highlands are those lighter, heavily elevated, incredibly ancient regions, and the fact that they're heavily cratered is not just a passing geographic detail. It is the entire context for why this dirt behaves the way it does.
Because craters mean impacts.
Exactly. Relentless, catastrophic bombardment by meteorites and micrometeorites for billions of years. Every single impact crushes, shatters, and pulverizes the bedrock. And that bedrock contains a massive amount of dark-colored basaltic rock.
Basalt, that's volcanic rock, right? Like you'd see in Hawaii or Iceland.
Precisely. It's an igneous rock formed from the rapid cooling of lava. So you have this volcanic, mineral-rich rock that has been smashed into a fine powder over eons. But here is the critical difference between dirt on Earth and dirt on the moon. On Earth, when rocks get crushed into sand, what happens?
Wind and water roll the grains around. They get smooth, like sea glass or the soft sand on a beach.
Exactly. But on the moon, there is no wind. There is no water. There is no atmospheric friction.
None.
So this dirt, this regolith, is composed of incredibly sharp, jagged, microscopic shards of glass and volcanic rock. It is incredibly abrasive. It holds a powerful static charge, and it is highly chemically reactive.
That paints such a wild picture. It's like microscopic, statically charged razor blades.
That's a very accurate way to put it. And the LHS-1 simulant is engineered to mimic that exact brutal composition. The researchers are trying to figure out how to feed the equivalent of statically charged volcanic glass shards into a delicate manufacturing machine.
It is the furthest thing from the smooth, uniform spools of plastic filament that you feed into a normal desktop 3D printer.
Oh, completely.
It really makes you appreciate the challenge of relying on a simulant. I mean, LHS-1 is obviously a brilliant scientific achievement in its own right, just to be able to recreate that highland composition in a lab. But it also opens up this whole avenue of speculation about the leap from the lab to the actual lunar surface.
How do you mean?
Well, the researchers are using this fake soil to practice, but how perfectly can we really emulate billions of years of cosmic history? Yeah. The actual dirt on the moon hasn't just been crushed, it has been baked by unshielded solar radiation. It's been bombarded by solar wind and subjected to massive temperature swings every single lunar day and night for millennia.
That is a very valid concern. It's a huge variable.
Right. While LHS-1 is the best stand-in we have, it makes you wonder what microscopic chemical quirks the actual historical moon dust might possess that a lab-made simulant might miss. It's like practicing a recipe with store-bought tomatoes when you know the final meal has to be cooked with tomatoes grown in a highly specific mineral-rich volcanic caldera.
Yeah.
It's close, but the environment leaves a fingerprint.
That is a brilliant way to frame the limitation, and it is a limitation the researchers are entirely aware of. You can synthesize the mineral composition of basaltic rock, you can crush it to the correct jagged geometry, but you cannot easily synthesize 4 billion years of continuous radiation exposure in an airless void.
So what happens if the real dust reacts differently?
Well, the real regolith might have microscopic iron nanoparticles embedded within the glass shards. Literally, vaporized iron from micrometeorite impacts that cooled instantly.
Wow.
Those nanoparticles could completely alter how the dust interacts with electromagnetic fields or the extreme heat of a laser. But you have to remember, the LHS-1 simulant is the absolute baseline.
The baseline.
Yeah.
Meaning if we can't do it with the fake stuff, we're doomed with the real stuff.
Precisely. If you cannot make the manufacturing process work with the perfect, uncontaminated, chemically identical lab equivalent, you have zero hope of making it work with the unpredictable, radiation-soaked reality of the lunar highlands. Shu, Wolf, and the Ohio State team had to prove the fundamental physics of the concept first. They had to prove that this chaotic powder could be transformed into a highly durable structure.
And they can't just mix it with water to make lunar concrete.
No. Because liquid water is arguably the most precious resource in space. You aren't going to waste it on mixing cement. You need a completely different method.
Which brings us to the technology they actually used. And this sounds like it was pulled straight from a sci-fi novel. It's called laser-directed energy deposition additive manufacturing.
It is quite a mouthful of a technical term.
It really is. I'm going to stumble over it.
Laser-directed energy deposition.
Right. But the underlying concept is just incredible. The researchers are using a special, highly concentrated laser to literally melt this fine, dusty synthetic material into layers, and then they fuse it with a base surface. And they aren't just melting the dirt on its own. The process involves precisely combining different feedstocks like metal and ceramics, during the printing process.
To manufacture small, heat-resistant objects, yes.
Okay, I want to try to visualize this for you. Think about a hot glue gun that you might use for a crafting project. You feed a solid stick of glue into the back, a heating element melts it, and you squeeze out a precise line of liquid glue that instantly cools and hardens into whatever shape you draw.
That's a good foundational analogy.
Now scale that up to an unimaginable extreme. Instead of a plastic glue stick, the material being fed in is crushed alien rock mixed with metals and ceramics. Instead of a tiny electrical heating element, the heat source is a concentrated, high-powered laser beam. And instead of crafting a diorama for a school project, the ultimate goal is building massive, sturdy, non-toxic habitats that will keep human beings alive in a lethal environment.
But the hot glue gun analogy only takes us so far, because melting rock is fundamentally physically different than melting plastic.
Right. I assume basaltic rock doesn't just cheerfully melt and flow like wax.
Not at all. The physics of laser-directed energy deposition, especially when applied to a geological material like LHS1, are incredibly volatile. When you use a hot glue gun, you are dealing with a polymer specifically designed by chemical engineers to melt at a low, uniform temperature and cool smoothly. Basaltic rock and ceramic feedstocks are not designed by nature to be cooperative.
So what does the laser actually have to do?
To melt these materials, the special laser has to generate immense concentrated thermal energy. We're talking about thousands of degrees, focused onto an area that might be just fractions of a millimeter wide. You are instantaneously transforming a solid crystalline rock dust into a superheated glowing pool of molten magma.
Wow. Tiny, localized magma pools.
Exactly. And as the laser moves along its programmed path to draw the shape, that microscopic pool of magma is left behind, and it immediately begins to cool and solidify back into a solid rock glass matrix. And this is where we run into a massive engineering hurdle. It's a concept known as thermal shock resistance.
Okay, hold on. Thermal shock resistance. Break that down for me. Explain it to me like I'm 5.
Imagine taking a thick glass baking dish straight out of a 400-degree oven and immediately dropping it into a sink full of ice water. What happens?
It shatters violently. I've actually done that, and it's terrifying.
Right, and it shatters because of thermal shock. When a material is heated to a highly energetic state like a liquid, and then rapidly cools down to a solid state, the outer layers exposed to the cooler environment cool down and shrink much faster than the inner layers, which are still hot and expanded.
So the outside is trying to contract, but the inside is still pushing out.
Yes, this creates massive internal stress. The material is literally pulling itself apart from the inside. If the material does not have high thermal shock resistance, that internal stress will cause the newly printed layer to instantly crack, shatter, or warp.
Which is a huge problem. You can't build a sturdy lunar habitat if your foundational bricks are shattering from the inside out just seconds after you print them.
Exactly. If the structural integrity is compromised at the microscopic level during the cooling phase, the entire macrostructure is useless.
Here's where it gets really interesting, because that exact problem, the internal stress, the cracking, the failure to create a durable structure, leads directly to the primary and frankly surprising finding of this entire research project. Suzeshu, the lead author from Ohio State, discovered that the final material is incredibly sensitive to its environment. But the breakthrough wasn't about tweaking the laser power or changing the dust mixture.
Yeah.
The real plot twist was about the ground they were building on.
The substrate dilemma.
Yes. The study revealed that the overall quality of the material depends greatly on the surface onto which the soil is printed. It's not just the ink, it's the paper you're printing on. The researchers tried to print this molten LHS1 mixture onto stainless steel surfaces.
And how did that go?
It was a disaster. Highly challenging, the researchers called it. It likely warped, failed to stick, or just fractured entirely. So then they tried to print it onto glass surfaces. Again, highly challenging. A failure. But then they tried a completely different base. They printed the superheated molten lunar simulant onto a surface made of aluminosilicate ceramic.
And suddenly, it adhered beautifully. It worked. The dirt and the ceramic played nicely together. The entire success of turning moon dirt into a durable structure relied entirely on the specific material of the foundation they were printing on. But wait, hold on. Why does ceramic work when heavy-duty stainless steel fails? Steel feels like it should be the strongest, most stable thing you could build on.
This is perhaps the most crucial scientific insight of the entire deep dive, because it moves us from abstract 3D printing concepts into hard atomic chemistry. Why did the stainless steel fail? It comes back to that intense heat and the rapid cooling we were just discussing. It involves something called thermal expansion coefficients.
Okay, you're going to have to translate that one for me too. Thermal expansion coefficient.
It is simply a measurement of how much a specific material expands when it gets hot and how much it shrinks when it gets cold. Every material has a different coefficient. Steel expands and contracts at a very, very different rate than basaltic rock.
Ah, okay. I see where this is going. So imagine you deposit a pool of superheated molten rock onto a room temperature stainless steel plate. The heat transfers into the steel. Now, as the molten dirt starts to cool down and tries to shrink, the steel beneath it is also reacting to the heat, expanding or contracting at its own unique, completely different speed.
It's like two people tied together trying to run in opposite directions.
Precisely. This creates an immense shear force right at the boundary layer where the two materials touch. The printed layer of rock essentially rips itself off the steel surface, or the stress causes the rock to turn brittle and shatter. The glass surface failed for similar reasons. It couldn't handle the thermal disparity.
Okay, so why is the aluminosilicate ceramic the hero of the story? What is it doing differently?
It's entirely different chemistry. Aluminosilicate is a compound made of aluminum, silicon, and oxygen. Now look at our lunar Highland simulant. The dark-colored basaltic rock is also heavily composed of silicates. They share a fundamental chemical family.
So they recognize each other, chemically speaking.
In a way, yes. When the laser melts the simulant onto the ceramic base, they aren't just two distinct layers sitting loosely on top of one another, like a sticker on a metal bumper. The heat causes the two compounds to interact, and they actually form crystals together.
Wait, they grow crystals?
Yes. They undergo a chemical reaction at the boundary layer. The molten rock and the solid ceramic interlock at the atomic level, growing shared crystal structures across the divide.
That is incredible.
It is. This deep chemical handshake is what enhances the thermal stability and mechanical strength that the study highlights. The base surface isn't just a passive table you're building on. It becomes an active, integrated partner in the structural integrity of the final object.
That is absolutely wild. So it is essentially welding with rock, but instead of melting two pieces of metal together so they pool, you are coaxing the molten dirt and the ceramic foundation to grow a shared microscopic root system of crystals.
That is a very elegant way to describe it, a microscopic root system.
It makes perfect sense why that would drastically increase the mechanical strength and the thermal stability. If they are chemically locked together with these crystalline roots, they can handle the immense stress of cooling down without ripping apart. But if we extrapolate that finding out of the laboratory and try to apply it to an actual mission, the implications for lunar-based design are just massive.
They alter the entire architectural paradigm.
Right. Because if this study proves that you absolutely cannot reliably 3D print sturdy structures directly onto steel plates, and you certainly can't print them onto glass, and you presumably can't print them directly onto the loose, chaotic, unmelted dust of the moon's surface without a proper base, how does that fundamentally change the architectural plans for a lunar settlement?
It suggests that the very first step of building a moon base isn't turning on the 3D printers to make walls.
Exactly. The first step has to be establishing an absolutely massive foundation pad of aluminosilicate ceramic. You would have to essentially pave the lunar surface with these specific, chemically compatible ceramic tiles before the massive laser deposition machines could even begin their work of building the habitats.
Which adds an entirely new layer of logistical complexity to the engineering blueprints. You aren't just bringing high-tech printers on a rocket. You have to figure out how to manufacture incredibly specific ceramic subflooring.
It's like realizing you can't build your dream house until you've invented and poured a completely new type of concrete slab.
You've identified the exact cascading logistical challenge that makes off-Earth construction so incredibly daunting. Every solution immediately requires a prerequisite solution. You want to build a wall out of dirt to save weight on the rocket. Great idea. But now you need a heavy ceramic foundation so the wall doesn't shatter due to thermal shock.
It never ends.
It doesn't. And this substrate dilemma, the realization that the printing surface is critically important, is really just one single variable in a massive chaotic equation. As senior author Sarah Wolf points out, there are a multitude of other environmental factors that heavily impact the stability of the final structure.
Yeah, the study found that it wasn't just the ground. The amount of oxygen in the atmosphere, the strength of the laser, and the speed of the printing process all drastically alter the outcome.
And this brings us to a harsh reality check about laboratory research versus field application. Wolf notes that conditions in space are really hard to emulate in a simulant. She acknowledges that while a highly specific combination of laser strength, print speed, and a nice ceramic substrate might work perfectly in a controlled Ohio State lab, a resource-scarce environment is a completely different beast.
It's one thing to make a souffle in a commercial kitchen. It's another to make it in a hurricane.
Precisely.
Yeah.
The technologies created for this kind of work must be engineered to survive what the researchers classify as extreme vacuum, dust, and thermal environmental conditions.
Wolf mentioned extreme vacuum and thermal conditions, and I really want to paint a picture of what those extreme conditions actually mean, because it is so easy to read the words extreme vacuum on a page and not fully grasp the sheer active hostility of that environment. Let's contrast the two realities. In the Ohio State Laboratory, the researchers have total godlike control. The room is climate controlled to a comfortable 70 degrees. The air pressure is a standard, comfortable 1 atmosphere. The electrical grid provides a perfectly stable, uninterrupted flow of power to the laser. And the LHS-1 simulant is kept pure and dry in sealed, clean containers.
A pristine sanctuary.
Exactly. Now, let's teleport that incredibly sensitive, finely tuned laser deposition machine to the lunar highlands. What actually happens? First, there is no air. Extreme vacuum.
Which is a nightmare for machinery.
Wait, why? Space is cold. Wouldn't a vacuum help cool the hot machinery down?
That's a very common misconception. On Earth, if an engine or a laser gets hot, the air around it absorbs that heat and rises, pulling cooler air in to replace it. That's called convection. In a vacuum, there is no air to carry the heat away.
Oh.
The only way for a machine to shed heat is through thermal radiation, which is much, much slower. A machine running a superheated laser in a vacuum will quickly overheat and melt its own internal components if it isn't perfectly engineered with massive radiators.
Mind blown. Okay, so it can't cool itself down. What about the external temperatures?
The thermal conditions are violent. The moon doesn't have an atmosphere to trap heat or block the sun's rays.
Yeah.
If your 3D printer is working in direct sunlight, the surface temperature can skyrocket to 250 degrees Fahrenheit.
Hot enough to boil water.
Easily.
Yeah.
But then, if a shadow falls over the machine star, maybe the shadow of a crater rim, or even the shadow of the habitat it's building, the temperature plummets to negative 208 degrees Fahrenheit within moments.
Oh.
Imagine the thermal shock to the mechanical joints of the robotic arms, the delicate glass lenses focusing the laser, and the highly sensitive electronics as they swing between boiling heat and deep freeze, sometimes multiple times a day depending on the orbit and location.
And then on top of all that, you have the dust. As we discussed earlier, it is abrasive, it is statically charged, and it is microscopic. It will cling to absolutely everything. Think about how a single grain of sand can ruin your phone screen at the beach. Now imagine statically charged glass shards grinding their way into the gears of the robotic arms, coating the laser optics, and contaminating the molten pool of regolith. The laboratory is a sanctuary. The moon is a chaotic, brutal war zone for machinery.
This raises an important question. And it's the exact question that Sarah Wolf addresses when she talks about the need to maximize the flexibility of a machine for different scenarios. In a resource-scarce environment where you absolutely cannot simply call a repair technician or order a replacement part on next-day delivery machine, flexibility is not a luxury. It is the absolute baseline requirement for survival.
What does machine flexibility look like in this context?
If the 3D printer is rigidly programmed to only work with a precise laser strength, a precise printing speed, and an exact atmospheric composition, it will fail the moment the lunar environment deviates from those perfect lab conditions. And on the moon, it will deviate constantly.
So it needs to be smart.
Exactly.
Yeah.
The machine needs to be intelligent enough, or at least adjustable enough, to sense its environment and adapt in real time. If a sudden temperature drop, say, that shadow we talked about, causes the molten regolith to cool too quickly and risk thermal shock, the machine needs the flexibility to instantly recognize that and increase the laser strength or slow down the printing speed to maintain the optimal thermal dynamics.
It's like driving a car. You don't just hold the gas pedal at one exact angle the whole trip. You adjust for hills, weather, and traffic.
Perfect analogy. If the local patch of regolith the rover scoops up has a slightly higher concentration of iron than expected, which changes a melting point, the system must adapt on the fly. Wolf's emphasis on flexibility is a stark acknowledgement that in space, rigidity equals failure. The technology cannot just be a blunt instrument repeating a single programmed motion. It has to be a dynamic, highly responsive system capable of surviving and operating through wildly fluctuating variables.
And understanding why this incredible level of technological resilience is necessary requires us to zoom out a bit. we need to look at the broader, real-world timeline of humanity's return to the moon and the economic realities driving these innovations, because this isn't just an abstract academic exercise happening in a vacuum, pun entirely intended. Thank you. This research is directly tied to the immediate future of space exploration. The researchers explicitly connect this technology to the NASA Artemis missions. And the stated goal of Artemis is establishing a long-term human presence on the moon by the end of the decade. We aren't talking about some distant Star Trek 50 years from now scenario. We are talking about a timeline that is happening right now.
And the entire strategic foundation for achieving that long-term presence revolves around an overarching concept that is essential to this discussion. In situ resource utilization, or ISRU.
ISRU. That's a term I feel like we are going to be hearing a lot more of as we push further into space.
Absolutely. ISRU is, simply put, the harnessing of local natural resources at mission destinations. Instead of bringing everything with you, you use what is already there. The logistical reasoning for why ISRU is so vital is straightforward. Additive manufacturing systems like this laser 3D printer rapidly reduce the need to transport large quantities of materials and heavy equipment from Earth. It theoretically enables astronauts to create an array of structures, tools, and habitats on demand.
Why is that such a game changer? Haven't we always brought our stuff with us?
We have, and that is exactly the problem. The paradigm shift, represented by in situ resource utilization, cannot be overstated. For the entire history of human spaceflight, we have operated on what we can call the camping trip model.
The camping trip model. Okay, break that down.
If you go camping in the deep wilderness, you have to pack all your food, all your water, your tent, your tools, your batteries, and your fuel. Everything you need to survive is on your back or in your truck. If your tent pole snaps in a windstorm and you didn't bring a spare, you're out of luck. Your trip is over or you freeze.
Right.
In space, that model is astronomically expensive and highly restrictive. Every single gram of mass you bring, every spare wrench, every extra structural beam requires a massive amount of highly explosive rocket fuel to lift it out of Earth's deep gravity well.
So a spare wrench might cost $100,000 in rocket fuel just to get it to orbit.
Easily. The Artemis missions are attempting to transition us from the camping trip model to the settlement model. When human beings historically settled new frontiers on Earth, they didn't bring entire prefabricated houses with them on wooden sailing ships. That was impossible. They brought the tools required to chop down the local trees and mine the local stone to build the houses once they arrived. ISRUs is the space-age equivalent of that historical necessity. The Ohio State researchers are essentially trying to invent the ultimate off-world blacksmith forge, lumber mill, and brick kiln, combined into one single robotic machine. If we can master this, we finally break the umbilical cord to Earth. The promise of these technologies allows for, as the researchers put it, extended independence as crews travel into deep space. We are moving from a state of total, terrifying reliance on constant supply chains to a state of profound self-sufficiency.
I want to spend some time really exploring the cascading benefits of that extended independence, because it fundamentally changes the safety profile and the viability of deep space exploration. Let's run a scenario. Imagine an astronaut on a newly established lunar base. They're out on a survey, and a critical structural support in their rover snaps due to metal fatigue. Or maybe a micrometeorite punches a small but dangerous hole in an exterior shielding wall of the habitat.
Very realistic scenarios.
In the old model, the camping trip model, like Apollo 13, what happens? They would have to radio Earth. Houston, we have a problem. They request a replacement part. They wait for engineers on Earth to design it, manufacture it, test it. Then they have to wait for a multi-million-dollar supply rocket to be prepped, fueled, and launched, assuming the weather in Florida is good. And then they wait days for it to transit to the moon. In a crisis, that kind of delay is lethal.
It's an unacceptable risk for long-term habitation.
But with robust, flexible ISRU technology, that entire convoluted terrestrial supply chain is bypassed completely. The astronaut simply shovels some local dark-colored basaltic dirt into the hopper of the machine. They input the CAD file for the broken rover strut into the computer, and the laser-directed energy deposition machine fires up, melts the dirt, forms those incredible crystalline bonds with the ceramic, and prints a perfectly fitted, heat-resistant, structurally sound replacement right there on the spot.
In a matter of hours, not weeks.
Exactly. If you don't have to wait for a supply rocket to bring a specific tool or structural patch and you can just print it from the dirt under your boots, the psychology of the mission changes. The safety margins expand exponentially. You are no longer living on borrowed time and strictly rationed supplies. You have the capacity to dynamically respond to unforeseen emergencies with virtually unlimited local raw materials.
And that capacity for dynamic response is exactly what is required if we ever hope to look beyond the moon.
Towards Mars.
Precisely. The moon is, in cosmic terms, our own backyard. A supply ship from Earth only takes a few days to get there if absolutely necessary. But if we are talking about human missions to Mars, a supply ship could take 6 to 9 months. And worse, it can only be launched during specific planetary alignments that occur every 2 years.
Wow! 2 years.
If a critical component fails on Mars, calling Earth for a replacement is absolutely not an option. You must be able to harness the local resources to survive. The moon, and specifically these lunar highlands with their abrasive, challenging regolith, is the ultimate proving ground for these ISRU technologies. If we can figure out how to force a laser to print durable ceramics and metals out of the chaos of lunar dust, while operating in a vacuum with massive thermal swings, then the technology will be robust enough to deploy anywhere in the solar system. The extreme constraints of the lunar environment force the engineering to become impossibly efficient and impossibly resilient.
Okay, let's take a breath because this all sounds amazing, but I know what some people might be thinking. What does this all mean for us, for you and me, sitting comfortably on Earth where we don't have to worry about the vacuum of space or the lack of a local hardware store?
It's a fair question. Why should we care about moon dirt lasers?
Right. It is easy to look at a highly technical aerospace study about building moon colonies and think it is just science fiction trivia, completely disconnected from our daily lives and our daily problems. But the final takeaway of this research brings this massive cosmic vision crashing right back down to our own planet, and the implications are profound. The researchers point out that the innovations required to survive on the moon could directly address some of the most pressing crises we face right here at home.
And it starts with energy.
Exactly. Let's look at the power limitations. Current Earth-bound 3D printing systems, like the one used in the Ohio State lab to run these tests, run on standard electricity. You plug it into the wall, and it draws power from the regional grid. But future space designs of this system cannot rely on plugging into a wall. The researchers suggest that to function on the moon, these massive, power-hungry systems must be scaled up using solar-driven or other hybrid power architectures.
Because you have to figure out how to generate the immense, concentrated thermal energy required to melt rock thousands of degrees without relying on a massive carbon-burning power plant.
If we connect this to the bigger picture, what we are witnessing is a masterclass in how extreme constraint breeds revolutionary innovation.
How so?
Think about it. On Earth, we have historically operated with an illusion of infinite resources and infinite energy. If we want to build a skyscraper, what do? We mine iron ore out of the ground, we refine it into steel using massive amounts of coal or natural gas, we transport that heavy steel thousands of miles using diesel-burning ships and trucks, and we assemble it using grid-tied electricity. It is an incredibly energy-intensive, wasteful, and resource-heavy process.
We do it this way because historically the resources in the fuel were cheap and abundant. We didn't have to be efficient.
But the researchers in this study are operating under the ultimate constraint: zero available resources other than local dirt and sunlight. If Siju and Sarah Wolf can successfully design a machine that uses highly efficient solar-driven or hybrid power architectures to manipulate the molecular structure of local dirt into high-strength materials, they haven't just solved the problem of lunar construction.
They've solved Earth construction.
Yes, they have inadvertently created a blueprint for ultra-low energy, zero-emission manufacturing. They are forcing the technology to become so efficient out of pure life-or-death survival necessity that it makes our current terrestrial manufacturing methods look archaic and gluttonous by comparison.
And both of the lead researchers emphasize this exact point. Cixie Xu is quoted saying, "There are so many applications that we're working toward that with new information, the possibilities are endless." And Sarah Wolf drives the earthly connection home even harder. She says, if we can successfully manufacture things in space using very few resources, that means we can also achieve better sustainability on Earth.
Gaining a better sense of how manufacturing might work in space could help researchers discover new ways to address critical material shortages back home. This is where the concept of sustainability gets a massive futuristic upgrade. I want to really explore what sustainability looks like if we apply this lunar resource scarcity mindset to our own earthly manufacturing.
It changes the definition of waste.
Exactly. Right now, when we face a shortage of a specific building material on Earth, say, there's a huge shortage right now of the specific type of rough sand used to make concrete. The global supply chain panics. We scramble to find new, pristine environments to mine and exploit. But what if we took the ISRU approach? What if we looked at the local, seemingly useless materials all around us the exact way astronauts are forced to look at jagged moon dust?
That is the exact conceptual leap the researchers are inviting us to make. True sustainability isn't just about using slightly less energy to produce the same traditional materials. It's about fundamentally rethinking what constitutes a resource.
Give me an example.
Well, on the moon, sharp, jagged, microscopic shards of volcanic glass are not a nuisance. They are the primary building block of civilization. If we bring that technology and that perspective back to Earth, we can look at environments and materials we currently categorize as waste or unusable. Think about the massive slag heaps left over from industrial mining operations.
Slag heaps. Those are the giant mountains of leftover rock after they extract the valuable metals, right?
Correct. Mountains of crushed, chemically complex rock that we currently treat as toxic eyesores. They just sit there leaching into the environment. Or think about the incredibly abrasive, unfarmable sands found in certain desert regions that are completely unsuitable for traditional concrete mixing because the grains are the wrong shape.
They're too smooth, usually,
Right.
right? Or too uniform.
Right, they don't interlock well for traditional cement. But if we scale up these laser-directed energy deposition systems that are powered by hybrid solar architectures and require no grid connection, and we program them with the extreme flexibility required for space, those massive piles of industrial waste and unusable desert sand suddenly become high-value feedstocks.
Oh, wow. I see it. We could theoretically deploy a flexible solar-powered laser printing machine to a depleted toxic strip mine. And it could just sit there and spend years silently melting the waste rock into durable, highly engineered structural components like girders or foundation blocks or even entire modular homes, all without drawing a single watt of power from the grid or requiring a single truckload of new, pristine materials to be shipped in.
The constraints of the moon force us to learn how to build beautifully and efficiently out of absolute garbage.
That is such a powerful way to frame it. The moon forces us to learn how to build out of absolute garbage. It completely redefines the concept of recycling. We aren't just talking about melting down plastic water bottles to make more plastic water bottles or park benches. We're talking about the atomic level restructuring of local geology and industrial waste into advanced sustainable architecture.
It is a stunning vision of the future, driven by the absolute necessity of surviving in the most hostile environment imaginable.
We have covered an incredible amount of ground today, from the microscopic jagged edges of fake moon dirt to the sweeping multiplanetary goals of the Artemis program. To recap for everyone listening, we started by unpacking the nature of the raw material, that LHS-1 simulant, designed specifically to mimic the dark-colored basaltic rock of the heavily cratered lunar highlands.
And the razor-sharp, statically charged reality of that environment.
Yes. Then we explored the mind-bending physics of laser-directed energy deposition, the process of melting that fake dirt and combining it with metals and ceramics to print layered, heat-resistant objects like a terrifyingly hot glue gun.
And the challenge of thermal shock resistance.
Which led us to the massive plot twist regarding the substrate dilemma. The fact that you can't just print on stainless steel or glass because they expand and contract at different rates, but that aluminosilicate ceramic creates a crucial chemical and crystalline bond that ensures the whole thing doesn't shatter.
A microscopic root system.
Exactly. Then we contrasted the pristine Ohio laboratory with the chaotic reality of the space environment. We talked about how an extreme vacuum means you can't cool the machines down, the wild thermal swings from boiling to freezing, the abrasive dust, and the absolute necessity of machine flexibility to adapt and survive it all.
A vital step toward in-situ resource utilization.
Right. We connected this technology to the grand vision of ISRU, the paradigm shift from the camping trip model to the settlement model that will allow Artemis astronauts extended independence from Earth's fragile supply chains. And finally, we brought it all back home to Earth, exploring how mastering the art of building with zero resources in space could revolutionize sustainability, power architectures, and how we view industrial waste right here in our own backyards.
It is a remarkable progression of thought, starting with a small pool of molten synthetic rock in an Ohio lab, and expanding outward to encompass the future of human habitation across the solar system. and then reflecting that knowledge back to solve our own terrestrial resource crises. The work of Zhu, Wolf, and their colleagues demonstrates that the quest to reach the stars is not a diversion of resources away from Earth. It is a profound investment in the advanced, hyper-efficient technologies required to protect and sustain our own planet in the long term.
Absolutely beautifully said. The push outward is what teaches us how to survive inward. And as we wrap up this deep dive, I want to leave you with one final lingering question to mull over on your commute, a thought that builds on everything we have discussed today. We have talked about how the harsh, barren dirt of the moon can be transformed into the very foundations of human habitats using advanced lasers and a deep understanding of chemical bonds. If we can master the art of turning a dead world's dust into a thriving colony, what completely unexpected, seemingly unusable waste materials sitting right here in our own backyards, perhaps materials you walk or drive past every single day and consider nothing but trash or environmental blight, might actually hold the latent, locked-away potential to become the structural building blocks of our next great sustainable cities. It makes you look at the ground beneath your feet in a completely different light. Thank you so much for joining us on this deep dive into the future of lunar construction and earthly sustainability. Keep questioning, keep looking up, and we will see you next time.